Doveva necessitare il puntino. Aparece el spotlight. Sí.
Pasar las diapositivas también. Estás aquí.
Sí, sí. Gracias.
Then welcome everyone. Today is a great pleasure to welcome and introduce Hugo Messias. So also particularly personally also for me to welcome him here. Well, I know Hugo since he was a PhD student, that's many, many years ago. So Hugo did his PhD in Lisbon in 2011. He then moved to Concepción in Chile for a postdoc. Then he went back to Lisbon for another postdoc for 3 years. Then he went back to Chile at ISO as a fellow. Then he went back to, guess what, Lisbon for a few months. And then, guess what, he went back to Chile since 2020, where he's an ALMA staff, ISO staff at the Joint ALMA Observatory. Hugo is working on all matters galaxy evolution related. When I have a question I don't know the answer to, I don't go to ChatGPT, I go to Hugo directly.
You got the ChatGPT.
He's also an expert on VLBI with ALMA. He's a member of the Event Horizon Telescope. And when you have your ALMA proposals approved, he's taking care of the phase 2 material for you. And today he's going to talk about something I didn't even know he was interested in. So I'll let him talk to you about it. Well, welcome. Hugo is here until tomorrow. So if you want to talk to him, last chance is today and tomorrow. He's in office 2508 or something, third paseo, first floor.
Thank you so much for Evanthea, and for the invitation and to be back here again, because I actually was presenting something about AGN selection while I was a PhD back when. So that was pretty cool. Let me just do something else. So basically, what I've been telling you about is something a bit that may be a bit contradicting. That is the neutral gas content in the ISM, but it's not going directly to the H1 line at 21 centimeters, but actually trying to infer its emission at high redshift. When I say cosmic noon is between redshift 1 and 3, 10 gig years old, 10 gig years ago, about ish. So this was a paper published last year with a great contribution from Andrea Guerrero and Jack Regueiro. They were actually undergrad and graduate students working with me, and really helped me, because the reason why is that the bottleneck of this study was actually convincing my collaborators that it could work. So actually having students that actually believe you a bit blindly was fun, because then it was good to start the work with that. But of course, a great contribution as also from the Concepcion group. So actually, in this work, actually, then I'll talk about one slide. Actually, this was potentially the first time that I work with someone trying to bridge the galactic knowledge that we have with what we see at high redshift. And for that is a contribution by Miguel Vioque, who's now in ISO working. So basically, let's start simple. So the full of galaxy growth is you start from neutral hydrogen. And then at very, very high redshift, you can have a molecular gas formation using electron or proton, but actually proton is even harder, but electron as a catalyzer, and it creates molecular gas, molecular hydrogen. And then because the conditions to form molecular hydrogens are also the good conditions to form star formation, stars. So basically that's why we see a dissociation, the great association between molecular gas and stars. After you let stars evolve via supernovae, AGB stars, or even growth in the ISM, you create dust. And as soon as you have dust, dust is the main catalyzer of creating molecular gas. But you can go actually back, because you can dissociate molecular gas either by stars, UV radiation, or actually collision as well. So you have a big of a mix here in this whole schema. Visually, this is how it looks like. So on the left, I'm just showing some fire simulations. On the left, you'll see UGR band color image, basically showing you blue regions are in and young are star clusters, and dust will appear in absorption. And then on the right-hand side, you'll start seeing magenta as the cold molecular and atomic gas, but then you'll see it predominantly turning into green as in ionized gas and or even red. So basically, this is how it looks like. It was evolving since redshift 30 or 20, and then you start seeing the galaxy growth. So basically, gas being locked into stars, but then also you'll see a lot of activity where it's the actual star formation activity starts pushing out some dust into the ISM, but also gas, and starts creating this greenish and red components. So this actually, sorry, let me go back. Okay, this actually is our simulations. Simulations are kind of more and more realistic, but they don't explain everything. But still, it's cool to see whatever you're seeing in the simulations. Actually, you can see this is the group, the 3 galaxy group, actually, where you can see that potentially they are not related, but actually then the H1 actually shows that there was already a passage and some interaction with the northern galaxy. Moreover, M82 is known for this these strong winds induced by star formation. So what you saw in the simulations kind of is seen here in reality. So if we want to identify all these points in this circuit, let's say, ideally we will detect them quite, I mean, we will try to detect them directly. But the problem is that all these things are not that easy to detect directly. So basically, with the neutral hydrogen, you can directly, but only at, until a given redshift. You have then H1 in absorption, but you need a background source. You have the optical and or ionized carbon and Schmidt-Chemical law to infer the H1 content, and this work as well. And then you have also molecular gas, which you have can have as tracer the carbon monoxide, atomic carbon, and dust. And then you have the star formation, which is with H-alpha, UV, infrared, or radio. And then you have stars, UV, optical, and infrared, and you have dust emitting in the far infrared and millimeter. So potentially you have all the mechanisms to do so. And when you do that, you actually have a really nice perspective currently nowadays up to very high redshift, so very early times in the universe. So you have the H1 on the top left, you have molecular gas on the right-hand side, and then star formation rates density on the bottom right-hand side, which you can already see that both of them are kind of peaking at redshift 2-ish, okay? And then if you integrate the star formation rate density, if you integrate that, then you can predict the amount of, then you can establish how much how much gas has been locked into stars, which is the middle plot here. But then with all these activities, you also produce dust, and it's also peaking at around redshift 1 or even 2. I'm saying 1 and 2 because both this one and the molecular gas might be affected by completeness. Okay, I'll talk about that if I do have the time to. So, but the problem is that I was saying that some of these components were peaking at redshift 1 and 2, right? But then if you look into the natural gas, it's just flat. You'll see some works trying to fit an evolution there, but so far it's pretty uncertain what is happening to the neutral gas. Okay, at very low redshift, at local universe, you see that the H1 content in galaxies has decreased dramatically. Not dramatically, but the problem is that as soon as you go farther, what you're relying on is actually on sub or Damped Lyman-alpha Damped Lyman-alpha absorbers, which require, again, a background source, a bright one. And for you to, in this case, the ones that have been identified as the absorbers have an impact parameter of between 1 and 100 kiloparsecs, while these estimates of the molecular and all the other components that I was talking about is tens of kiloparsecs at most, okay? So how do you do that bridge between one and the other? So for that, because, and on top of that, I go back to what I was saying, direct detection of H1 and H2 is hard. So how do we try to go about that? So with H2, I was mentioning already, it can be directly detected in hot regions, but it won't be representative, and it's very hard to do so. But then you have the CO, atomic gas, and carbon, atomic carbon and dust. But then the H1, you can directly detect it up to redshift 0.2, 0.4 now. There were some results with fast, that is almost 0.4. There is a lens detection up to redshift 1.3, but that's basically about that. There were some works doing a stack analysis up to redshift 1.5 as well, of tens of thousands of sources, and they did detect something. But then after that, it's just you're relying on absorption, right? Or relations. You know, in the optical, in the atomic ionized carbon up to redshift 4 or 5 that these people have used. But yeah, so basically, let's try to go back and see what can we do more than this. So what people have now long realized is that the mass locked into dust very much relates with the ISM mass. So the mass of the ISM gas. So molecular plus atomic hydrogen. And depending on what sample you use, you'll see a somewhat tight relation to it, okay? But so here is a way for you to just tracing the far infrared and millimeter, you can infer within a factor of 2, 3, what's the content of the ISM. So what's the fuel that is still out there to fuel the galaxy growth. But if you know that measuring the dust mass is very hard. You have degeneracies between the dust mass and the dust temperature, and you really need to trace the far infrared plus the millimeter to actually do so. So the other trick here is actually you go to the optical thin part of the SED. So in this case is 850 microns, so almost 1 millimeter. I know there are extreme cases where there's optical thickness even up to 2 millimeters. I know, but it's not really the overall population. But because it's optically thin, then you can have an estimate of the dust mass, and the scatter is purely related to temperature. Okay, but still, even if you don't know the temperature, the scatter here is actually very small. And the relation between dust mass and the optical thin part of the Rayleigh Jeans part of the SED is actually quite tight within the relations that we are used to in astronomy. So this was actually something that has started to be used and is now so-called the Scoville relation, which you actually can try to use this data point of the SED at rest frame almost 1 millimeter, and then infer the ISM. Nowadays, the way people are using is a direct relation between millimeter continuum and CO luminosity, but as I will show you, is not the best relation. So here's this, with this localish sample that I'm trying to show you, is the relation between L850 and CO luminosity, and the sample that I'm using to fit is the grayish data points, and the yellow are higher redshift samples, like 0.2, 0.3, that were not used for the fit and just showing where they fall within this relation. The blue line is just a ratio between the L50 luminosity and whatever is in the x-axis. You'll see what I mean. And then the red line or shaded region is just the best fit to that cloud. So now I'm showing you just L850 850 luminosity with H1 mass. The relation improves, but now I can put it both together, which was what I was talking about. So H50 luminosity versus ISM mass, and the relation improves a little bit, and I can do the trick that it's not the first time that people do, is actually I let the alpha CO. So basically here, what ISM by mass ISM mass, what I mean is the helium contribution, the atomic hydrogen and molecular hydrogen, and this alpha CO, which converts CO luminosity into molecular gas. We know that depending on the galaxy properties, this alpha CO is known to change. More specifically, what we currently believe is that it changes with metallicity. Here with this sample, I don't have a way, especially because not this sample, I don't have a way. What I mean is that if I want to apply this to high redshift, it's very hard to get the metallicity estimate. So here I will not take that into account. I will just use a single alpha CO, but I can actually let it free in the relation, and actually it converges. If I let it free, it converges to a value of 1.1, so lower than the galactic, which is this 2.9. You've heard about 4 because it's 1.36 times 2.9. Okay, that's the galactic value. I will go through this on the implications of using 2.9 and 1.2 later on. But basically what you've seen is that you started from this relation and now you have a much tighter one. And you can see that the yellow stars actually fall right on it. A little bit lower, but within the scatter. Okay. So this 850 luminosity versus the mass ISM holds for 3 decks, 3 orders of scale, and within a factor of 2. So what is also showing us is that this red, which is the best fit to the relation, also will predict larger ISM masses. And what's the implication of that? Because as soon as you have in surveys, almost surveys, you will have the continuum, the dust continuum. So you have L50, and you'll have also, in some cases, if you do a blind search of CO or you know the redshift, you'll have also the CO luminosity. So this, in that relation, which is this one that you see, you have this, so you have the y-axis, and you have the LCO of this relation. So you can invert things into inferring the H1 mass. So this is a trick that we've applied. Now, curiosity. This is not the first time that we do it. So in the 80s and 90s, a similar approach was actually used to infer whether there were regions in the series of the galaxy that did not have CO emission, but did have H2 contents. Later on, people have been used also this kind of trick to actually in-resolve galaxy samples to see how the alpha CO changes within the galaxy. So what we are doing now is actually establishing a common relation and try to see if how it applies and what are the implications to apply this to the high redshifts. So some caveats before we go on. This one is very important, which is collocation. In our own galaxy, you'll see the stars and the dust in absorption. You have the star formation here via free emission. You have the odd dust and the molecular. They follow quite nicely each other. But then the longer wavelength emission of the dust is everywhere. And so it is the atomic gas. Okay, this part is the series, not the greatest component of the overall H1 content or the dust mass, but it's to show you that you should be careful about collocation. The other thing is that at higher redshift, Milky Way may not be the most representative galaxy in the universe, of course. So do we see also this in other galaxies? And actually we do. This is the scale height of the with Herschel, and the longer wavelength that you have, the biggest, the puffiest is the galaxy. It depends also on stellar mass too. At higher redshift, you see that the dust continuum, rest frame 250, is smaller than the size of the molecular gas and stellar emission. So the other thing is that how it evolves, all these sizes evolve with infrared luminosity. At high redshift, you see that potentially there's a decrease in size with luminosity, but it's actually not clear because other ones actually show an increase. So people still do not agree. What is clear, and here is a nice plot, is that these sizes, these dust sizes at high redshift are much bigger, like a factor of at least 4, about by I'm doing by now. But with it they are bigger than whatever you see in the local starbursts. And yeah, this is just a comparison with UV and C2, where here, for instance, at high redshift with atomic carbon, the far infrared is larger than the UV, but smaller or comparable to the atomic carbon emission. So what I want to say, it all depends on sample selection method and rest frame wavelength that you're tracing. So the caveat number 2 is the error budget. So you saw that the dust, I'm doing a relation that is kind of hopping from relation to relation. So it's dust plus CO to infer the H1 relation. And then also there is, I'm relying on the relation on the lowest, so the ground transition of the rotation transition of CO, so CO1 to 0, but these higher redshift surveys identify CO2 to 1 and 3 to 2, so I need to convert it. So we need to convert it back down to 1 to 0. So that also induces a little bit more error. The overall flux absolute flux uncertainty between surveys, so that's about 10%. And then the uncertainty on the dust spectral continuum, and then cosmic variance. This to say that this relation is very dangerous to use on a one-to-one basis, but if you use it on the statistical basis, as you'll see, I think for me, it's safe if you have enough galaxies to do so. So the other thing is completeness. I've mentioned this before, but what I'm going to show you is not a complete assessment of H1 content in the ISM at high redshift. And because this, as you saw from the relation, I'll be based on the CO plus dust selected sample. And that will basically miss the low metallicity galaxies, which tend to be high, rich in H1. So up to 90% of the ISM can be in H1 phase, sorry, in atomic hydrogen phase. And then the other thing that we need to keep an eye on is that the calibration is done with local samples and with ISM maps up to 10 to the 11th, but some of the prediction are kind of going above. So you can see this as an extrapolation in some of these cases. So this is, of course, relation dependent. So basically what we've done is to go through the literature and find as many samples as we could where we have dust and CO detections. So really massive thank you for all the contributors to all these samples. So we go from local 0.2 with Veils up to redshift 5 and 6 with, for instance, Phoebs and Phoebs 2. Okay. Sorry, Walter as well. So, so yes. So what you'll see later is that I'll be focusing, when I talk about H1 content, I'll be focusing on two samples, the aspects and the Birkin, because those are the ones that the selection function is easier to know. The other ones were previously selected in optical with optical spectra, sometimes optical colors. So it's very hard to actually then infer the completeness of those samples based on all those properties. So let's start with the results. So in terms of gas ratios, overall, we see a 1-to-1 relation or a 3-to-1, depending on, remember that you had the blue relation, which was just a ratio between the H50 luminosity and the ISM mass. So using that simple ratio, we have a 1-to-1. So basically, overall, in the galaxy population, you have as much gas in H2 and H1 at higher redshift. This can be up to 3-to-1, but I'll go through that about comparing the relations. But again, it all depends on selection function. If you go to different samples, some might have a different ratio that I'm reporting here. I'm talking about the overall sample that we got. So it's about 335 galaxies that we saw. But you can see from the upper left plot that, actually, you don't see my mouse, but upper left plot where actually there's a scatter of plus or minus 1 order of scale. So, but in terms of depletion times, what is telling us is that if you actually go straight to, okay, I have this molecular gas because it's easier to measure, and I have this star formation rate, so the depletion time is just a ratio of the two. Is that no? Wait, because you still haven't been accounted for the H1. Some people even account for the helium. So if you account for the helium, why don't you account for the atomic hydrogen? Okay, so that's a factor of 2 right there. And the other thing that people normally don't take into account, because this ratio of molecular gas over star formation rate is too simplistic, is that it's the GMC physics. So at least based on what we see in the local universe, is that GMC timescales are actually between 10 to 30 mega years, while the efficiency, star formation efficiency, I mean, how much mass you convert of that whole GMS into stars, it's between 2 and 10%. But this ratio, if you actually play around, actually this ratio is the same as you using the 10 mega years and a 5% efficiency, or 20 mega years and a 10% efficiency. But if you actually use the median values, then already it's another factor of 2 that you're losing there. Okay. So at higher redshift, people have been showing that potentially this efficiency is larger, so it kind of levels out. But depending on what you're doing, it may be a danger. It may be a danger. So what we've proposed is actually this relation, which has, if you only have the star formation in H2, then you have to put 2 factors, whatever you believe your sample has. One accounts for the missing, for the atomic hydrogen that you don't see or you haven't measured, and the other one is the GMC physics. So I can give you some examples with some sources later on in the questions. So in terms of mass functions, on the left-hand side, upper left-hand side, you have the molecular gas mass functions. The crosses are our estimates, and the shaded regions are the literature values. I'm not accounting for helium here. But what we've done here to establish these data, because nowadays you actually on the upper left plot, you see these boxes. That's what people are now doing the luminosity function with CO. Okay, because it's so low number statistics that people have to do like this, right? But then what we've done actually is something that is used in the in some works in establishing H1 mass functions is actually remember that the error budget I was telling you is very large. So what we do is it's sort of a probability distribution function, and we put different probabilities for a single galaxy in different mass bins. And this is why we are only presenting crosses in specific ranges. If you are suspicious about it, don't worry, people are sometimes, but I'll show you later on how does it look if I just use this if you want. But yeah, now if I do that with the H1 predictions that we have, the Vmax, so the volume that a given galaxy contributes to this is based on the CO luminosity and the L50 luminosity. And this is what you get. So on the upper right plot, the dashed line is the local mass function. The shaded region is an H1 mass function based on the B band's luminosity. So it's a relation established at high redshift, and then you grab the luminosity function of B band and you convert it into H1. This was done by I need to let me go back because yes, Chowdhury 2024. But what's is clear is that above 10 to the 10.5, 10 to the 11, you see a clear detachment between whatever you see in the local universe and what you see in the high universe. So basically what you see actually is a strong decay of H1 content in galaxies on the most massive ones. I'll go through that as well. So in terms of H1 mass density evolution, what you see in blue is the H1. This is, I've presented you already, that this is the literature, and the box are the so molecular gas content, and the blue is the H1. And you think that potentially you can see an increase of H1, but if you actually select in terms of luminosity, so you compare apples with apples, actually you see a decrease. Overall, you see that this sample is recovering between 15 and 20% of the total that you see as super Damped Lyman-alpha. But then if you actually do a cut in the lurg level, actually you see the triangles. And this is what I want to show, is that the triangles seem to decrease. The blue triangles, which is the H1 of the most luminous galaxies, seems to decrease, while the black ones either flatten or increase, but the errors are a bit larger. Then I realized I had missed this paper also from Chowdhury, is that actually they found this with much better significance at slightly lower redshift. What they found is actually the average of H1 in galaxies above 10 to around 10 to the 9 decreases dramatically between redshift 1.5-ish to redshift 1. So what this is telling us, different samples, different selections are telling us that whatever is inducing the decrease of star formation since redshift 1 is actually the lack of gas inflowing into galaxies, namely H1. You stop having enough H1 in the ISM of galaxies to form more molecular gas and to form more gas, more stars. Now, I still have time, right? Yeah, okay. So you've heard me talking about two relations. So the ratio, which is simpler, and the linear relation, which is the best fit into that cloud that you saw. Currently, my expectation is that the ratios, so the RT, is regarded as the more realistic, since the linear relation predictions reach 90% of H1 gas ratios. That's dwarf and high Z-like, nothing like the high massive galaxies at cosmic noon. The H1 cosmic content of this linear relation predicts actually reaches the total in some conditions, which for me is not credible. But both of them predict very high H1 sizes. So locally, you have a very tight relation that compares the amount of gas that you have in a galaxy and its size. And if you apply this relation to the predictions that we have, you have potentially sizes of half a megaparsec, which is crazy, right? You do have the gas being expelled and seen in simulations up to those sizes, but it's like actually being able to relate that into future star formation is a long shot, okay? So actually, if you can play a trick, which is we know that galaxies are smaller at high redshift. Actually, the groups here in IAC have been actually working tremendously on that. You can actually decrease this constraint down to 80 to 200 kiloparsec sizes. This is correction dependent from this work, Buitrago and Trujillo, 2023. So, but for you to have a reference, the largest spiral galaxy in the universe identified so far is 200 kiloparsecs. So it's already kind of within ballpark. So yes. So now why 2.9 and why 2.9 versus 1.2 in terms of the alpha CO? So the factor that converts this CO luminosity into H2. So there's things, I mean, CO is actually collisionally excited by by molecular gas, and that's what you adopt as the relation to, okay, CO is a nice tracer, but it's not, because it can also be collisionally excited by atomic hydrogen, helium, and even water in some cases. So this is this I actually didn't know the water, but in some conditions you can have also this type of collisionally excitation. So my perspective in this relation right now is actually the alpha CO in the equation actually is a way to correct for this. And if you see, this is the Schmidt-Kennicott law, and you can see that this region, especially this region here, is known to be where there's a balance between atomic hydrogen and molecular hydrogen. Apart from that, is actually either you're dominated by H2 or dominated by H1 in different scenarios. So, but if I actually do use 2.9 in the relation, you saw that the error bars were large. With 2.1, 2.9, it even decreases more. So the conclusions that I've showed you kind of washed a little bit, but it's the same. I mean, you're using the wrong relation. Of course, you'll get less clear results. And again, the metallicity dependency on alpha CO were not accounted, but I can show you plots where I talk about that. So the other thing is the predictions of H1 line fluxes with this ratio relation. You can see that what I'm showing you here is the line peak flux predicted by these relations for all the sample that we've considered compared to the SKA1 1 hour sensitivity. Okay, this is the dotted line. These lines that are here are just telling you the mass threshold. So basically, what it's telling us is that the ratio here is predicting for some of these galaxies up to 10 to the 12. So that's a lot of gas in H1. But what it's telling us is actually, this is 1 hour of on-source SKA1. You actually need 100 hours to actually start seeing the top of these galaxies, the top distribution of these galaxies. So actually the strategy of Chowdhury that have been using a lot of GMRT data is actually, even with SKA1, will actually be, if you know how to classify and characterize your initial sample in terms of completeness, then it can be a way it's stacking. So this is basically what I'm in terms of numbers. So for 100 hours of one source, no overheads counting here. The ratio method is actually predicting 120 120 galaxies per square degree at redshift between 1 and 2, and only 8 between redshift 2 and 3 directly detection. So I leave you with the conclusions. I think I'll go through that very quickly. So we have used this relation to actually predict H1. So it's two tracers to infer the atomic hydrogen. The observed gas ratios overall is 1:1, but it's sample selection dependent. But it's already telling us that if you actually consider that and the GMC physics, you're probably underestimating the time, the depletion time by a factor of 2 at least. And then the H1 mass functions are showing us that the greatest change in H1 content is actually above H1 masses above 10 to the 10.5, 10 to the 11. There's a sharp drop, as we saw from the GMRT group, but also that drop is actually seen even at high redshift for the brightest galaxies. And we are probably, this sample is possibly detecting up to 20% of the overall H1 content in the universe. And yes, you'll probably need stacking to actually get most of the galaxies with the SKA1. Thank you.
Questions in the room? No? Oh.
Very nice talk, Hugo. I'd like to know a little bit more about SKA. I mean, you say that you need about 100 hours on source, etc. So how does actually SKA works? I mean, it works in survey mode and also in dedicated follow-up, or how is it?
So in from 2026, I believe they will start working up until 2028. I think the timeline is that one, that they will start working on the surveys that they will conduct. And I do believe that there will be some strategy like the one that you're saying, like in survey mode, because you can basically with the precursors, you're already doing that. With the MWA and with the ASCAP, you're serving the whole sky. And then you have deeper fields, and I think they will do the same with SKA. It just those precursors on steroids, but still, even with SK1, we'll just be having a direct view of these most massive galaxies that can be directly detected. And I don't know about how much it will be, but I would say that the surveys, depending on what you're trying to do, I think because actually this was something that it was not clear at the time, but actually these frequency ranges, from what I understood, it will be an instantaneous. They will have instantaneous access to this range. So every time you're doing a survey, you're doing a survey at the same time in all this range. So that's why I didn't correct these values. But yeah, these are the numbers. At cosmic noon is not very, I mean, at redshift 2-3 is not very inspiring. This is the lower thing, but I mean, it's 8 plus or minus a big factor. If you see it's 8, but it can be 38, so it can be 40. So it really depends on what's happening here.
Thanks very much for this very dense.
A lot of information.
You probably said it, but sorry, I couldn't absorb everything. So you said this greatly depends on your sample, right? So and you mentioned you were using aspects and the Walter samples.
Birkin.
Birkin, yeah. So what samples are these? So how does the sample selection affect your results?
I mean, it can go different ways. I mean, you can be overestimating if you don't know well the sample selection. Then the Vmax method can either predict too small of a volume, so you count more that a given galaxy, and for the overall H1 content, or if you can go other way. So it's really hard to give you an answer of what's depending, but it's just based on, for instance, the optical selection. The optical selection of some of these samples, you start with color selection, and then you go to the observatory to get a spectrum, and you will not get spectrum for all of them. So how do you account for this completeness?
Okay, so there
So
maybe
this is the hard part of using the other ones, while the blind surveys with Birkin and with aspects are easier to control.
So basically, because you have a handle on the selection function and not because of the actual nature of the selected
No.
sources. That's what I meant.
No, yes. It's
Okay,
just
right.
how easy it is to actually.
Okay.
So since, I mean, again, this was a very kind of not short in the dark, I want to say, but it's like, it was already hard to convince my collaborators that this could work. So trying to convince with a referee with a very dodgy way of trying to correct for the sample selections of these other samples is very hard. So yeah.
Thanks for the talk, Hugo.
Yeah.
Very nice. So I'm not sure if I fully understood
Mm.
at the beginning when you
Yes.
explained the method, no, the trick that you used. So regarding the alpha CO, no, you show two plots. So okay, so what you do at the beginning? So for some galaxy, you have the H1 content, right?
So for this sample is
You have
a
both,
local
no? You have
sample where
CO.
yes, you have the three.
You have
parameters.
everything.
Yes.
So then you put them together, you feed them, and the alpha CO that you have there, it's the alpha CO that you measure from.
So if I let it free,
Yeah.
if I let it free in this sample, then I get 1.21. If I fix, so
If you fix it, no, it's
it's
2.9 because it's the galactic value.
Yes.
Mhm. And if you let it free, it goes to 1.1.
Yes. So there's more to that. So let me actually share you more plots about that. So this is the second part. So this is me trying to, because for this sample, I don't have the methodicities for all of them. So what I try here is actually through a series of relations, I try to get the metallicity, and with that, I get the alpha CO. And it's a bit scattered. There's still a trend there, but it's a bit scattered, I believe, because of the many relations that I'm using to get the alpha CO base depend on that. So the second is what if I try to split this sample into galaxy properties. So because this local sample has everything, okay? It's all the galaxies that we found back when, up to 2017, actually that had all the three parameters. So it's everything, it includes mergers. So, but actually if I then exclude no major mergers and no minor mergers, I get a sample of 132 instead of 169, but the converged value, it's still around 0.95. It's only when I actually cut the sample into the very narrow part of ISM mass of between 10 to the 10, 10 to the 9, which is kind of Milky Way-ish, then you get an increase of 1.5, okay? But still not the 2.9. So that's why I believe that, I believe now, after reading a little bit, I understood that the L50 is not really tracing the ISM mass. It's tracing most likely the radiation field. So that's why this is not completely a complete tracer of the ISM mass, because here you're missing a fraction of the H2 because you're dropping a little bit the alpha CO. So, but the H2 mass function that I showed you, I assume the 2.9, because that's what we see overall. I mean, it's, but if you want to use this relation, then this is what's happening. It's many things taken into account. Is that it's the radiation that is actually hitting the dust for you to see the dust, and the second one is that CO is excited, collisionally excited by many things, and not just molecular gas. Yeah.
Okay, thanks.
Yeah.
That's it. Last question. I guess.
Online.
No, online there is nothing. Well, I'll show you something now, but later.
Okay.
Yeah, so we can thank the speaker again.
Thank you so much.
Stopping, you paid for it? Yes. No, there is no